Hello, everybody. This is Qing Shuo Song from Worcester Polytechnic Institute, and my talk is about solving elliptic HJB equation with deep neural network, and it's a joint work with Wenhao Chu, my master student, and George In, University of Connecticut. We have three parts in this talk. The first part is problem setup, second part methods and analysis. The third part is numerical results and summary. All right, in the first part, the problem we're considering is a stochastic control problem. So we have a controlled stochastic differential equation starting from x. So the initial state x, and the stochastic differential equation has shift b, which is controlled by a. And dws is random part, which is Brownian noise, and tau is the terminal time. And we have a total cost along the path. Of course, this depends on which state you are starting with and which control you are going to use to drive your path. So you can think of something like this. Here is a domain, and you are starting from some initial state x, and you can choose some smart strategy A to drive your path in the future, and sometime you will hit the boundary. Then you can compute the total cost along the path, which is defined through the running cost L and the terminal cost G. Now the objective is to find optimal A, which minimize the total cost, which is defined as V. So this is called the value function of the control problem, and this is what we want to find out. All right. Usually this kind of value function is associated to the elliptic HJB equation, which is fully nonlinear PD, and there's no explicit solution in general. So people think about computational method to approximate the value function. And our approach here is based on Markov chain approximation and deep learning. So for the Markov chain approximation, we recommend Kushner and Dupé's book in 2001. And our recent work here is about how to adapt this Markov chain approximation to the recent development in neural network. Before we start, we need a benchmark problem. By benchmark problem, we mean an example with specific domain and specific running cost, terminal cost, and we are able to give analytic solutions. So the purpose of benchmark problem is to compare with our numerical solution and evaluate its performance, its approximating performance is good or not. All right. The second part, methods and analysis. To start with, we first recall the verification theorem. So this theorem says if you are able to find out the solution of HJB equation given here, then this is exactly the value function of the control problem. And we said, first of all, this is second order differential equation because there is the second order term, second order differential operator term. And f given here is nonlinear because of minimum, so it's hard to solve it. Now, Markov chain approximation, it tells us how to discretize the previous HJB equation and try to come up with MDP, which is Markov decision process. So suppose we have H as discrete parameter. Then we discretize the domain first, and then use central finite difference scheme to discretize HJB equation, which goes to Perlman equation. This is quite magic, and that defines MDP. And the theory says that, well, if you can solve MDP, then you obtain approximated value function. So the task is to solve MDP. And the traditional methodology about the MDP is value iteration and policy iteration. In this work, we are going to adapt this MDP to neural network. So suppose the neural network is given, which is denoted by psi, and theta is the space of parameters. So for the neural network, the simplest example for two layers, suppose d equals 1, so dimension is 1, so you have one number as input. Then it can, the input will be fed into the first layer, and then second layer, and then gives output, which is output. So we write y as psi x, which is a function of x. But this depends on the parameter of the connection between layers. So we have a lot of parameters. And the function of psi depends on what kind of theta you have. And there's another one key factor for the neural network is activation function. So suppose you have neural network, then that means you have a class of candidate function for the approximated value function. And you are going to choose the best one. To do that, we first propose a loss function. The loss function is a sum of two parts. The first part is to gauge the performance of approximation interior of domain, and the second part is the loss to gauge the approximation behavior at the boundary of the domain. And sum up, you have total loss function. So if your candidate function gives minimized value of the loss function, then it's gonna be a good approximation. So in other words, for the computation, there's a tolerance, and you're going to find some theta h, which makes the loss function within this tolerance. And by the neural network gives a function corresponding to theta h, which is approximated value we are looking for. All right, here is a pseudocode. So we have neural network. It depends on what activate function or how many layer, how many neurons you adopt. And we give a tolerance, very small number. And we start with flag true, which means as long as the true value for the flag, then you need to repeat the rest of the block, which is actually stochastic gradient descent method. So this is SGD. So by repeating this, we can have the loss function smaller and smaller until it falls into the tolerance. And then we can switch the flag into false, and then we quit. That gives the numerical solution. The theory says that, all right, so if h is small enough, then the approximated value from neural network is supposed to be very close to v under some assumption. And those assumptions can be explicitly verified from our example. And the proof relies on viscosity solution approach from monotone scheme and stochastic approximation. All right, the last part. We can quickly go over one-dimensional example. So for one-dimensional domain, that is it's a line, unit line, and we use 8 meshes, equally distributed, and we use 2 hidden layer and 18 neurons and ReLU activation function that defines the neural network. And the result is pretty good. And this is loss function. When the epoch reaches like 2800, then the loss suddenly drop into some satisfied level and stabilize. And there are many more examples implemented and uploaded to this GitHub. If you're interested, you're welcome to visit that site. All right, the summary is that, well, we proposed numerical solution based on MDP and neural network. However, from numerical experiment, we can find that stability is not good enough. And in particular for high dimensional problem. All right, thank you very much.